For practice here, you might as well finish around. By the way, the student pointed out in the problem session that there's a free version of MATLAB available, and it's called Octave. And so, those of you who don't have MATLAB on your PC or laptop can download it from their website. It's probably www.octave.org, but the easy way to do it is to Google Octave, and you'll then find out. And it in some ways, it's, well, I don't have enough experience with it to know. And it turns out that one low temperature experimentalist, a Russian by the name of Dmitry Sergatskov, who used to work in this department, very smart guy, is one of the developers of so I sent him an email and asked him, what do you think of it? And he said he was biased. All right. So we were talking about Fourier series last time, and we had gotten to the point of, well, let me just review some of these. Basic idea is that we have these vectors E sub n, and we can expand any function in terms of these vectors, n going from minus infinity to plus infinity. The inner product of x with En here is e to the I nx over the square root of I. And then the coefficient Cn is just En, the inner product of En with f, which is the integral from, let's see, what was the integral? 0 to 2 pi. One can think of this as En x, x f dx, and so that's integral 0 to 2 pi e to the minus I and x over the square root of 2 pi f of x dx. So that's what that was the basic idea. Then we saw that we could write the Dirac delta function as, now when you say the Dirac delta function, that's actually an abuse of language. There are many Dirac delta functions. Distributions are maps that map spaces of functions onto numbers. And so when you change the space of functions, you change the distribution. And so what's a good Dirac delta function for one space of functions won't necessarily be a good Dirac delta function for another space of functions. And the same thing for any distribution. So for this particular interval, 0 to 2 pi, and the functions that are suitably smooth, then the Dirac delta function can be written as sum n equals minus infinity to plus infinity e to the in x minus y divided by 2 pi. And another way of thinking about that is just the inner product of x with the identity operator written as n equals minus infinity to plus infinity e sub n y. All right. So we learned those things last time, and we also learned that the interval, well, we have the integral from 0 to 2 pi, but we could just as well have an integral from minus pi to pi, or for r to r plus 2 pi. The important thing is if we divide by square root of 2 pi, then we want the interval, and we have the INX, then we want the interval to be a length of 2 pi. Now, if the function happens to be periodic, then you can use any old interval, and then it won't matter, because if the function f of x is equal to the function f of x plus L, then you could write this as integral 0 to 2 pi e to the minus I and x over the square root of 2 pi f of, say, x minus L dx. Well, L was a bad choice. L suggests the length of an interval. Let us say x minus well, let me just think. Actually, x minus r, just any r, would work. Maybe I should make that a homework problem. Anyway, you can shift the interval by I guess what happened, well, you can shift the interval, but when you shift the integral, it may be that the coefficients change, so let me not write this as an equality here. It is an equality, of course, if you shift the length of periodicity. And I mentioned where to put the 2 pi's is an issue. The simplest way to do it is to just use the square root of 2 pi and then the square root of 2 pi's occur all over the place, but this equation, which gives you x hat or f of x equal to the sum of Cn from minus infinity to plus infinity e to the I n x over root 2 pi. So as I said, you can, if you want, if you multiply this by square root of 2 pi, then you have to divide by the square root of 2 pi there. And that's a possible way of doing things. In fact, an alternative way is you divide here by square root of 2 pi, and then when you've done that, there isn't any 2 pi that occurs over here. So the example that I'm going to do is the function f of x equal to e to the minus m times the absolute value of x, where m is just some real number. And we're going to use the interval minus pi to pi. So in this case, we have these coefficients dn. I'm using d instead of c to emphasize that we're going to have a 2 pi here rather than the square root of 2 pi. So then this is the integral minus pi to pi dx over 2 pi e to the minus I and x e to the minus m absolute value of x. So these are the coefficients, and the series now will be, that's the interval. So we'll be representing this series as the sum dn e to the I and x from minus infinity to plus infinity. Writing an equal sign here is not really appropriate. We should do something else, maybe put a tilde over it, because the equality only really holds for within this interval unless the function is periodic of period 2 pi. If it's periodic of period 2 pi, then and the series converges, then it's actually an equality. Okay, well, if we do this integral, it's the integral minus pi to 0 dx over 2 pi e to the minus in, sorry, that's an n, minus m, whoops, actually a plus m. That's a plus m. And then it's the integral 0 to pi dx over 2 pi e to the, let me just read the notes, e to the minus m plus I n x. And a better way of writing this is the way it's in the notes. I don't know why I do it extemporaneously. M minus I n x. So, in other words, when x is negative, the absolute value of x is minus x, and that cancels the minus sign, and that's why it works out like that. Well, we can we can do these integrals. This is just 1 over m minus I n times this evaluated at the two limits. And when you do the arithmetic, you get 1 over pi, the number m over m squared plus m squared times 1 minus 1 to the n e to the minus pi m. So that's the formula for e sub n. Now, a couple of things can be noticed here. First of all, P is real, so D of n is D of n star, and this is an n here. This way it makes it clearly an n. Moreover, the thing is an even function of n because of the n squared here, and minus 1 to the n is the same as minus 1 to the minus n. And so d sub minus n equals d sub n. And so we have the condition d minus n equals dn star, which is the condition for, on the coefficients for a function that's real. That's something that we showed previously, that if f is real, then Cn star is C of minus n. Okay, so we verified that at least the function, the coefficient d sub n, satisfy the reality for the condition. And now the Fourier series then is e to the minus m absolute value of x is a sum n equals minus infinity plus infinity en e to the I n x, and that's the sum from minus infinity plus infinity 1 over pi m over m squared plus n squared 1 minus 1 to the n e to the minus pi m e to the I n x. So that's our formula, and we can simplify it somewhat. Namely, you can pull out the case for n equal to 0, and that gives you 1 over m pi 1 minus e to the minus pi m, and the rest of them you've got, you see, since dn is equal to d minus n, you have e to the I n x and e to the minus I n x have the same coefficient d sub n. And so that gives you a cosine. And so this is equal to plus 2, the sum n equals 1 to infinity of 1 over pi m over m squared plus n squared, again these funny coefficients, minus 1 to the n, e to the minus pi m cosine of nx. So now the functions are manifestly real. I should be using the overhead projector to show you this. There's a figure in the online notes. Let's see, does anybody have the online notes in his laptop? No?
Yeah.
Yes?
Oh, but it's somewhere.
All right, I was going to say we might connect it to that and then I can show through the projector.
You could try. I don't know if it'll work. It's on my Linux, so I don't know how well that'll work with the second monitor. You could try. I've never tried it before.
All right, why don't I pass this to you? And
maybe I'll just download it on Mac.
the other thing is, I think I need to get the clicker.
I can get it here. It'll work easy in my Mac. Linux, I don't think it'll work on the whole. What's the website?
That's his. Oh,
I'll just download it real quick. That'll be easier. Because the Mac will work easy.
oh, okay.
Linux doesn't always work.
Is this?
Oh no, I don't have it. Never mind.
You don't have the right.
I have the high definition one. I need a converter. Yeah, that's right. I lied. What about that guy?
Oh, just a little bit. Yeah.
Maybe if you sat here. All right, maybe I should go get the clicker.
What about you? You're sitting there.
What? I thought you were working. I can't get wireless. I don't have it saved on my hard disk.
Oh, you don't have the notes on it?
I don't have it saved because it keeps updating them.
Yeah. Oh yeah, mine would have been an old version. Anyway.
Yeah. I just get them off the web, but it's wireless here sucks.
You can get it right off the door. You can't get it in here. How do you turn it on? He wants to stand on a chair and push the button. What do I put here? So you're saying typing in Mathematica is faster than writing with your hand?
Oh, no, writing faster. It's just that for classical mechanics, we also have those, yeah.
Oh, you want
Well,
to
it is like-
Yeah, and then I just started developing a habit that I'm going to really organizing if I do
That's
everything.
painful.
So, I don't know how to turn that on. I don't have
Stand on a chair and push a button.
a. I don't know what?
A chair and push a button. There's usually a power button on them somewhere, right? Or am I
Let's see,
lying?
don't you can find a pointer so somebody doesn't risk his.
Well, I can't reach him for sure.
Who's tall?
Maybe the gray chair next to
Actually, this is a stable platform.
this. You have to get this.
The liquids out of the way.
This has to be on tape. That's the most important part of what's
I
going
don't
on.
even
Is there a power button? I could have lied. There's a big switch on the side.
You should just be in standby right now, though.
Oh, that's the wrong.
Click that again. That'll turn it back on.
push it the other way?
Yeah. Because it should have been in standby before.
That sounds fancy.
And which of these buttons I can...
It may just turn on.
Maybe the one with the blinking light next to it.
It stopped blinking.
It'll come on now.
Yeah, it's on now. It's on.
Yeah. Okay. All right. So. Okay. Well.
So you'll see the type of notes in LaTeX you have to do the homework to every day, right?
Oh, we run the notes every week.
Homework's due every day.
What do you mean the notes that are?
Wow, you got it. Wow, that's great.
Case classes?
Yeah, you have to type.
So we take notes in class and we have to type them up in class.
But
Why?
I mean, you could sit here. We could put it on there, or you could sit in front of it. Which is better? It's more stable.
Oh, it doesn't come out too well.
Yes.
Okay,
I
so
wouldn't want to see that. It's lost in class.
I mean, it's hard to see anyway, too.
so what you see here is this is the Fourier series for the case where m is equal to 2, and 10 terms gives you the solid curve, which is red. And you see it goes back up like that. Now, the actual function, e to the minus 2x, looks like this, about 0. It's just a decaying exponential, and because it's absolute value of x, it decays in both directions. On the other hand, the Fourier series for this, we're doing the interval minus pi to pi, so that's like minus 1.5 to 1.5. I'm sorry, minus 3 point something. To plus 3 point something. The Fourier series is going to be periodic and of period 2 pi, and so once you get past pi, it then starts to repeat so that it follows this curve here. And then similarly, when you get below minus pi, it imitates this curve to achieve periodicity. So it only resembles the function e to the minus 2 absolute value of x on the interval from minus pi to pi. But with 10 curves, it does pretty well. With 100 terms, you have the green curve, which is really, really very close. And in fact, with 100 terms, in the interval between minus pi and pi, the 100 term is very, very close to the exact result, which is this blue dotted curve. The exceptions are that as it gets near these ends of the interval, minus pi and pi, then you see the 10-term curve starts to wobble. The 100 curve, if we had better resolution, we'd see that the 100 curve is maybe not quite so good. And then, I guess they both do pretty well here. This is just a 10-term that's not so good. All right, so why don't we put the lights back on and go a little bit further in the chapter. Are there any questions? All right. Now, as I said, I chose to do complex Fourier series before doing the real Fourier series because they're so much more symmetrical and consequently so much easier to learn. On the other hand, if you feel that complex numbers are spooky, then you prefer the real Fourier series, and that's what I'm going to discuss now. So if the function is real, so f and f star are the same, then as we've seen, c minus n is cn star. And in particular, C0 is C0 star. So C0 is real. And then this function, f of x, can be written as C0 plus the sum e to the in x c sub n plus, this is the sum n equals 1 to infinity plus the sum n equals minus infinity to minus 1 e to the I n x c sub n. And you see there isn't any square root of 2 pi here, so I'm using this convention for the 2 pi's. Okay, so this is C0 plus the sum n equals 1 to infinity Cn e to the I n x plus c sub minus n e to the minus I n x. So we can combine the two sums. This then is C0 plus the sum n equals 1 to infinity. And now this is Cn e to the I n x plus Cn star e to the minus I n x. This is because the function f is real. So this only works for real functions where c sub minus n is Cn star. So c sub minus n is Cn star. Now we expand the exponential. Remember, e to the I theta is cosine theta plus I sine theta. And so this is equal to C0 plus the sum equals 1 to infinity Cn, maybe I should use a square bracket here, cosine nx plus I sine nx plus Cn star, cosine is even, so this is just cosine nx minus I sine nx, sine being odd. And then we can combine the Cn and the Cn star and so forth, so it becomes like this. C0 plus the sum from 1 to infinity of Cn plus Cn star times cosine of nx plus I Cn minus Cn star sine nx. Okay. So that's the expansion. But now we don't want, obviously, these Cn's are the coefficients that were appropriate for the complex Fourier series. And so for real Fourier series, we make some redefinitions. We write the complex number Cn as a half an minus I bn. So an is equal to Cn plus Cn star. Bn is I Cn minus Cn star. And then, just erase some of this, then the Fourier series has its standard real form. Which is to say, f of x equals a0 over 2, and I guess I should put that. Sum n equals 1 to infinity a sub n cosine nx plus b sub n sine nx And the formulas for an and bn are, well, an is cn plus cn star. And remember, as I said, we chose to use one of the 2 pi convention where the 2 pi only occurs once. And so this is integral 0 to 2 pi dx over 2 pi e to the minus I n x f of x plus e to the I n x f star of x. But f star is real, and so this is equal, f is real, I mean. So this is integral 0 to 2 pi dx over just pi f of x times e to the I n x plus e to the minus I n x over 2. I grabbed the 2 and put it there. This is just the cosine formula, and so this is equal to the integral 0 to 2 pi dx over pi cosine nx times f of x. All right, are there any questions? Of course, one obvious question is what's the formula for Bn? And again, Bn is I Cn minus Cn star, and so that gives us Bn is equal 0 to 2 pi dx over pi I e to the minus I n x minus e to the I n x over 2 half of x, and you can rewrite that as integral 0 to 2 pi dx over pi sine nx times f of x. So that's our formula for B sub n. And the formula for, let's see, what do we have? A0 is 2C0, and C, that means that that's 2, the integral dx over 2 pi 0 to 2 pi e to the minus I n x, but n is 0, so that's just 1, so it's just f of x. And so C0 then is the integral dx over pi f of x. And actually, now that I think about it, the reason why I didn't write it explicitly is that this is the correct formula for A0. So A0, A0, 2 is cancelled. So A0 is dx over pi. That's 1 when n equals 0 f of x. So it's just the kind of an average value of, it's half the average value of f on the integral. So that's, or is it twice? Let me see. Yeah, it's twice. Twice f bar. Now, just as we derived our formulas for the complex Fourier series from the orthogonality relations for those functions e I n x over square root of 2 pi. So too, the orthogonality relations for the sines and cosines can be used to derive the representation of a real function in terms of real Fourier series from these relations. 0 to 2 pi sine mx sine mx dx equals pi or 0 n equals, whoops, n equals m, not equal to 0, and we'll just write else, whatever, n not equal to m or n equal to 0. Here, 0 to 2 pi cosine mx cosine nx dx equals pi of n equals m not equal to 0, 2 pi n equals m equals 0, and 0 or otherwise, else, and then finally n equals 0 to 2 pi dx sine mx cosine nx is simply equals 0. By the way, let me ask the class a question. Do you prefer integrals to be written, definitely written this way, dx at the end, or do you like it better 0 to 2 pi dx and then the integrand there?
Doesn't matter.
Doesn't matter. To me, it doesn't matter either, but to some people it matters, and I might as well do it the way people like it. So
It seems like at the end is what.
I never realized why people put it next to the integral anyways. I mean,
you mean why people do this?
yeah, I mean, it's like, it's if you have a big complicated expression, you have to be careful with your parentheses, whereas if you put the dx at the end, it's pretty obvious, you know, what's
Right.
going on.
That's the advantage for that.
Right.
You're right. But suppose you have a doubling.
In that case, I usually just put like in my limits, I just say x equals log on the limits, and that makes things clear.
That's annoying.
Really? Isn't that bad?
Yeah. I mean, in other words, what I'm saying is, if you do integral 0 to 1 dx, integral 0 to 2 dy, f of xy, then you sort of know who's doing what.
Right. What I'm saying is, what I
If
do
you put
is,
these guys at the end,
You have to go back and look at your calculator.
I'm saying to resolve that, what I say is like on the limits, you could say like x equals 0 to x equals 2 or something like that. Clarifies it. I don't know. That's just me. I just whatever.
all right, well, if it works for you, that's fine. I think what I'll do then is, to please everybody,
In the middle.
most as best I can, I'll try to put the dx at the end because it's a multiple integral. On the other hand, that may be more confusing. Maybe it's better to have them all the same. All right, let me just remind you, though, the thing that I think is probably the most confusing thing about the Fourier series. Namely, what if the function f of x is not periodic? Well, the Fourier series to the function is always periodic because it's a sum of functions that are periodic with period 2 pi, whether the real functions cosine nx and sine nx, or the complex function e to the I nx, those functions are periodic with period 2 pi. So the Fourier series is always periodic, period 2 pi, with these functions. On the other hand, if the function itself, if you're representing, is not periodic, then the series is going to be periodic, the function is going to be periodic, and that's the example that I illustrated in the e to the minus mx case, e to the minus m absolute value of x, that we did on the board with the help of your technology. Okay? So that's something to keep in mind. All right, so let me, in fact, now we have another example, so let me work out the mathematics, and then we'll turn out the lights and see what the computer gives. Now, I solve these things just by using Fortran, which is my usual way of doing things, although I sometimes use Maker MATLAB, mathematical, and now Octave.
Is Fortran numerical, or is it only numeric? Or is it...
Yeah, it's and it's a very good way of doing numerical. There's vast libraries, and it almost is a language, or a computing language with training wheels. In other words, you can make mistakes. Writing in any computer language, there's a tendency to make mistakes. But there's bugs. But with Fortran, I think you tend to make fewer mistakes. And moreover, if somebody's reading somebody else's Fortran code, you can sort of follow it. Whereas if somebody's writing in C, people love to get cute with C, and then the other guy is reading the code has no idea what's going on. And I'm told, somebody told me that with C++, it gets even worse, because C++ is a language that's designed for people who really know how to program. And most physicists have never taken a course in programming. They just learned it on the fly, learned it on the street. And so, and I'm in that group also, in programming class. And it turns out that with C++, if you're not trained in computer science, you tend to write bad code. Anyway, sorry for the interruption. So now we're going to write a function f of x equal to x. What could be simpler? And we're going to use the interval minus pi. Okay. Now, the function x is obviously not periodic. So the function f of x equal to x does that. Then we might have, there's 0, there's minus pi, there's pi. Then we expect our Fourier series to do pretty well here, but as soon as it gets beyond that, it's going to try to do this again. And as soon as it gets to minus 2 pi, it's going to try to do that. So the series is going to be trying to do this. I should have brought the colored chalk today. And the function is this. So you only expect the series and the function to agree between minus pi and pi, which is generally what's the case. Is generally the case. If the function is not periodic, you expect it to be well represented only within the interval. And here it's going to be dramatically different. At least, though, the coefficients aren't too bad. I'm using those formulas over there, then b sub n. First of all, a sub n is equal to 0. Why? Right. It's an odd function, and so the ANs would be the integral of an odd function times an even function on, well, that might not be the case here, but we're on an interval that's symmetric about 0. So on an interval symmetric about 0, in other words, this would be the integral 0 to, well, it's minus pi to pi, dx over pi cosine nx times x. And so that's clearly 0. Pn, on the other hand, is integral minus pi to pi dx over pi x sine x. And of course, I violated the rule that I was going to use. That's good. And anyway, this is 2 minus 1 to the n plus 1 times 1 over n. And so what we have then is a series. X is approximately represented by the sum n equals 1 to infinity, 2 minus 1 to the n plus 1 sine nx over n. So this is, whoops, This is our function. So now let's look at what the curves actually turned out to be. I'll turn out the lights. Oh Christ, the thing went black again.
It goes on standby after a while.
It goes what?
I think it just sleeps after a while.
Gee, if we only had a pointer. All right. Somebody tell me what to do.
It must be the button that's next to the blinking light, maybe. Try that.
Maybe we should flip the switch back and forth.
Yeah, that would. I think it takes a while to start up too.
If I hit the button again.
Let's go.
Should I hit the button?
I don't know.
One more time.
Huh?
Go ahead.
Yeah, something's coming on, I think. No. All right, we need some advice. What should I do?
Flip the.
It's on.
There you go. All right. All right. Okay, so let's look at these series. So here's what we see is that between minus pi and pi, it's okay. But then the Fourier series drops down in order to be periodic, or jumps up in order to be periodic. And so let's just see what we've got here. Let me find the caption. 10 terms, it's red again, and you see the overshoot. You see the function, the Fourier series gets really nervous here because it knows it has to jump all the way down there. So it overshoots and undershoots. This is called the Gibbs overshoot, the same J. Willard Gibbs. And then with 100 terms, you see the overshoot doesn't occur prematurely. It occurs only where it really has to do the crazy thing of jumping down. And then with 1,000 terms, you have the blue dashes. And the upsetting thing here is that the Gibbs overshoot doesn't go away as you use more and more terms. Instead, it just gets closer to pi and closer to minus pi and so forth. The function f of x is the thing in purple dots that goes along there. Okay, so the series is periodic, the function is not. Okay, so we'll turn on the lights and go to the next topic. The next topic is stretch intervals. So far we've been saying, well, we can move our interval from the 0 to 2 pi, or minus pi to pi, or r to r plus 2 pi, but we've always kept it a length 2 pi. And now we're going to change that, and we're going to make it of an arbitrary length L. And this is a very, it may sound trivial that we're just switching from 2 pi to length L, But this is the essential thing that you do when you go from a Fourier series to a Fourier transform. You take L to infinity. And we'll do that in the next chapter. Okay. Here's a nice picture. All right, so stretched intervals. Okay, so we go from 2 pi to L. And what we want to do is, I'm going back to the complex exponentials because those are the easy ones to use. And so we have 0 to L, first orthonormality, 0 to L, e to the I, 2 pi nx over L, over square root of L, complex conjugate. Well, we don't need parentheses. EDI 2 pi mx over L over square root of L dx equals what? It's equal to delta nm. So we have an interval of length L, and clearly when n is equal to m, these phases cancel. You just have 1 over L. The integral of 1 over L from 0 to L is 1. On the other hand, when n and m are different, then you do the integral and you have a denominator that has n minus m in it, and then the thing that gets integrated is e to the I 2 pi x over L times m minus n divided by, what is it? It must be I 2 pi over L m minus n, but this is evaluated between 0 and L. At 0, this thing is 1. At L, it's e to the I 2 pi times an integer that's not 0. Well, it doesn't matter if it's 0, but it's not 0. That's also 1, so 1 minus 1 is 0. So for n not equal to m, you get 0. And the reason why this formula is correct for n not equal to m and not for n equal to m is obviously when m is equal to n, this formula is infinite. So this formula is true only when m is not equal to n. All right, so that's our orthonormality relation. Then we have f of x. We're going to write it as this sum from n equals to minus infinity to plus infinity, Cn EVI 2 pi nx over L over square root of L, and then these coefficients Cn are the integral 0 to L e to the minus I 2 pi nx over L divided by square root of L f of x dx. So those are the formulas that are the analogs for length L of the formulas of the complex exponential on the integral of length 2 pi. Okay. Now, if the function f is periodic, then we can shift this domain of integration. And that's what I wanted to do over here, but somehow I wasn't thinking. We can also say, so if f of x plus or minus L is equal to f of x, then the C sub n is equally the integral from R to L plus R, e to the minus I 2 pi x n over L square root of L f of x dx. So you, in other words, you can either use this or that, and the difference is that these two functions are periodic, so it really doesn't matter whether you integrate from 0 to L, the thing maybe goes like that, but then at L, it drops down to this. Wait, now I have to. All right. So it doesn't matter whether you integrate from there to there, or you go from, say, this point to that point. Okay. All right. I have a little bit of an offset here, but you see what I'm saying. Maybe I should use a function that's. Let's use a function that's sort of obviously periodic. So this is 0, and that's L. Let me just do this. So this is a trivial example because it's a sine function. But it doesn't matter whether you integrate the sine times another periodic function from 0 to L, or you go from pi over 2 to pi over 2. You see, you get this integral there, but doing it this way, this part makes up for what you missed over here. All right. So you can shift you can shift the interval and still have and when you do that, you don't change the coefficients at all. If the function is periodic. If the function is not periodic, though, then when you change the interval, your coefficients can go crazy. They can be very, very different. Any questions about that? So now, if we put this all back together, what we have is f of x is then the sum minus infinity plus infinity on n, so n equals cn e to the I 2 pi in x over L divided by square root of L, and then we can rewrite that as n equals minus infinity plus infinity e to the I 2 pi and x over L integral 0 to L dy, and now the two square root of L's combine, and you have e to the minus I 2 pi in y over L. That's y. And we can rewrite that as an integral 0 to L. Here, I'll write the dy over there. And then 1 over L sum n equals minus infinity plus infinity e to the I 2 pi n x minus y over L f of y dy, and we can say then that delta of x minus y is 1 over L sum n equals minus infinity plus infinity e to the 2 pi I n x minus y over L. So this is the representation then of the Dirac delta function that's appropriate for suitably smooth functions on the interval 0 to L. And in fact, if this is really a function perfectly as a Dirac delta function, then I think you want to say it's functions that are periodic of period L and defined and suitably smooth and defined on the interval 0 to L. So it's with that class of functions, this is a good delta function, a good representation of delta function. Anyway, this is what I call stretched intervals. And why don't you jostle it a little bit so maybe it'll wake up.
Yeah.
This did, and that way I would have to get up on the table. By the way, can you make this image be the whole screen? Some trick for doing that, I don't know. I'm not a Windows. I use Linux instead of Windows, so I don't know what advice to give.
So 2 icons to the right of the 100%, there's a little.
There you go. Keep going
To the right.
There you go.
There, that one. Try that.
You can make it in presentation mode, right? So it's like F5 or I don't know.
I don't know if you can do it in the
F5?
web browser.
Yeah, there's like
Yeah.
a. Oh, is it?
She's
Is it a
in
browser?
browsers, so.
All right, well, we can live with this. It's okay. All right. Now we can make use of this delta function. Well, let me give another expression for this delta function. We can combine certain terms here. The n equals minus n and the n equals n. Combine them together, we get a cosine. And so this thing can be written as delta x minus y is 1 over L plus 2 over L, sum n equals 1 to infinity, cosine of 2 pi n x minus y over L. So that's another way of writing this delta. And if we go back to this formula, which is a simpler, more symmetrical formula, see, with the reals you always have these asymmetry, sine, cosine, and 0 is always a special case. So it's really kind of annoying. But let's suppose we have a function f with coefficients cn, a function g with coefficients d sub n. Then the sum n equals minus infinity to plus infinity of cn star d sub n, well, is the sum n equals minus infinity to plus infinity. Cn star is going to be 0 to L e to the Cn star now is e to the I 2 pi n x over L over square root of L f star of x and dx, and the other one is integral 0 to L e to the minus I 2 pi n y over L g of y over square root of L dy. And so this is then the integral 0 to L dx, integral 0 to L dy, f star of x, g of y, delta of x minus y, the Dirac delta function. And then that is just integral 0 to L dx, f star of x, g of x. And in particular, if f is equal to g, then we get the rule that the sum n equals minus infinity plus infinity cn absolute value squared is equal to the integral 0 to L absolute value of x squared dx. This is called Parseval identity. And this has actually there's something deep lying beyond, something very nice lying behind this. Notice that if this integral converges, then the function f is said to be square integrable on the interval 0 to L. And if that integral converges, well, this sum has to converge. This is a sum of positive terms, or at least non-negative terms. This sum then converges. So what we can say is that if the function f is square integrable, it's on the interval 0 to L, it's representable by a Fourier series, the absolute value squares of whose coefficients converges. Some of the absolute value squares of the coefficients converges to a finite number. Is what convergence is supposed to mean. And so the space of square integrable functions is a natural space for Fourier series. It's also a natural space for Fourier integrals, but there the square integrability refers to the real line. So if the function is square integrable on the real line, then it has a Fourier transform. And in fact, in this case, the analog of this will turn out to be that the Fourier transform is also square integrable on the real line, and the two integrals are equal. We'll learn that in the next chapter. I just want to foreshadow that. Okay. Well, if the function is real, then we have these real versions of, so if f equals f star, then what we have is f of x is a0 over 2 plus the sum n equals 1 to infinity a sub n cosine 2 pi and x over L plus b sub n sine 2 pi and x over L. So those are the real relations, and a sub n then is 2 over L integral 0 to L cosine 2 pi and x over L f of x dx, and b sub n is 2 over L 0 to L sine 2 pi and x over L f of x dx. And these follow from the orthonormality relations, which are they're analogous to those. Why don't we? Can you skip to the orthonormality relations instead of my writing them on the board? Right. So here are the orthonormality relations. The integral 0 to L sine 2 pi mx over L, 2 pi nx over L is L over 2 if n and m are the same but not 0. Otherwise it's 0 because sine of 0 is 0. 0 to L dx cosine mx nx L over 2 if they're equal but not 0. L if they're equal and 0. 0 otherwise. And then sine, the sine of one and the cosine of another is 0. Always. Okay, well, the next topic is to generalize all this to, what the heck, why don't we do that? To several variables, and I then, for some reason, decided to also double the integral to 2L so we could go from minus L to L. And then the orthonormal functions are e to the I pi n dot x over L divided by 2L to the capital N over 2. Capital N being the number of variables. And then the series goes from N1 goes from minus infinity to infinity. N2 goes the sum from minus infinity to infinity. And N sub n goes from minus infinity to infinity. Then the coefficients Cn are integrals over all of space f of x times the complex conjugate of this basis function, integrated from minus L to L. And so this is the form that you want for the general Fourier transform, because then these coefficients then are, you just let L go to plus infinity, minus L go to minus infinity, so you have the integral over all space, and this pi n over L you rewrite as a vector k, a wave vector, and well, we'll see that in the next chapter. I think though we ought to pause for questions and then quit. I assume, by the way, let me just ask as a question: is it better to see this written on the board with chalk, or do you prefer it on the screen?
Sometimes when you write it on the board, you take intermediate steps, which are nice, or you'll kind of explain it.
Yeah.
And I know I appreciate that because I can read the notes and
That's right, you can read the notes anytime.
and kind of when you make addendums to it or you talk through a particular logic step,
Okay.
that's appreciated.
All right, are there any questions? All right, well, let me stop the tape then.
Unless, of course, you were direct.
I did meet Dirac once and heard a lecture on him once. That's about it. In fact, he was sitting next to Wigner. Wigner was sitting next to each other on the couch, and this was shortly after some physicists had proven that a certain quantum field theory was actually finite, ultraviolet finite. And I knew that Dirac had always quite rightly emphasized infinities in quantum field theory, and although you could renormalize them away, they were really a serious problem. And so I said, what do you think about this result? Neither one of them said a word. They just sat there on the couch. Well past 80.
I got this for
Want to go stop by your office?
Yeah.
And start
All right.